15-20 minutes, and then we'll open the floor for discussions and any questions that arise from it. Just to recap on what Jason has said, this is feedback on a kind of a research project that we did. And I would say I'm talking about GTI and EcoSource in collaboration with Amy. Amy's based in the UK. They were funded through Innovate UK, and we were funded through the Technology Agency, Innovation Agency here in South Africa. And the idea was to look at the opportunities that are presented by the integration of two new technologies, and actually to showcase this to water authorities. And as Jason explained, we worked closely with them. Gainey, you did share some data sets with you. We have augmented that actual data with synthetic data to help with the actual valuation, but we're going to show you the results of what we did and how we set it up and what it actually means. Okay, so it's all to do with using artificial AI based data insights linked to satellite derived intelligence to augment what you already have and give insightful information into what is happening in a water management system. Okay, so let me just move my screens across so I can get the point of moving through. Okay, so we started from the premise that information management and information usage is a big challenge, not only in water authorities, but in this case, a water authority being the targeted group, but in most organizations. So you actually have thousands of reports and logs, complaint records, sensor data that needs to be integrated and utilized in order to gain insightful intelligence, which can be used then for actionable sort of scenarios going forward. Okay, a lot of that data in many organizations, again, water authorities, is unstructured. By that, what we mean, it could be in written report format, it could be scanned PDFs or scanned graphics, it could be logs, it could be emails. Okay, so that poses a challenge in terms of tracing back any particular problem within the system back to its root causes, because you've got a whole disparate set of information in databases that would have to be looked at and linked together in order to gain those insights. So you kind of have a very limited cross-functional visibility of what actually could be intelligence within the system. And this process that we're going to show today has been designed and is designed, and in many cases is semi-operational, some of it, to actually show that capability. Okay. So what we've done is to show how we can take what is called the Insight Engine, which is an Amy product generated in the UK, with WaterSphere 360, which is a satellite-driven water information system with monthly updates, which has been developed by EcoSource and GTI, and pull those together so that you actually get this integrated information capability and information extraction. Just to kind of give you the background to this in terms of what Insight Engine is. Insight Engine is a operational capability developed by Amy in the UK, and it's built around using AI-driven data extraction to extract and derive additional intelligence and insight from a whole range of data in a whole variety of different databases. Okay, they've worked very closely with many water authorities in the UK, and it has been focused as a product development on water authority support. Okay, to kind of put that into context, it's very much like taking ChatGPT and internalizing it within your system. Okay, it's definitely not linked to external parameters, external links, and so on. So it only works within and is situated within the company database. So it doesn't compromise anything in terms of security and privacy going outwards. What we're showing you is something that we've run within the Insight Engine within Amy, by just borrowing data from Gainey and augmenting that with additional synthetic data from ourselves. So this was never placed within your system. This is actually a proof of concept mock-up to show you how it actually works. Okay, and the great thing is that because it's AI driven, it has the capability to identify the hidden data links, the associations between disparate sets of information that allow you as a user or a management group to actually possibly start to have better understanding of cause and effect relationships in the system that you're managing, using information which is both structured and unstructured in format maybe often contained within separate components of the whole database. So it's designed to create new actionable knowledge and insights that it wouldn't normally be able to access or create. The AMI Insight Engine, as I said, is operational. It's already used, but without WaterSphere, in Anglian water, Northumbrian water, and Yorkshire water, for exactly the reasons that I've expressed. Okay, it's AI-based integration of a whole range of different data sets, giving them analysis, predictive insights, things like leak detection, operational efficiency, and the strategic planning. It's working for them. Okay, so this is not a concept. This is actually an operational tool. What we've done here in this particular research kind of focus project is to link this with WaterSphere to show what those two together can give you. Okay. WaterSphere 360, if you haven't heard of this before or come across it, is a globally scalable monthly water information service that between EcoSource and GTI we've developed and now operationalized with funding from the European Space Agency. For those that know the Mzansi system here in South Africa, that we've been again jointly operating for the last 6 years through the Satellite Application Centre to support a lot of government levels of government tiers of information and universities and so on. This is Mzansi taken to the next level. Okay, so in addition to understanding every month where water exists in terms of surface water extent and giving qualitative dam and reservoir volumes based on image detectable water characteristics, we've actually now added rainfall trends, vegetation condition, which can even then talk to food security in terms of cropping activity and crop condition, and also changes in groundwater and soil moisture. And all of those collectively are then used to create and inform the service users of the drought risk. And obviously with the data sets we've got now going back between 10 and 20 years, you've actually got long-term drought profiles that can be generated and actually understand where we're going to and where we are now. Okay. In addition to that, the service also creates what is important in terms of this demonstration, monthly water quality. So it's an estimation of water quality in a given dam for a particular month. This is similar to, but quite different from the weekly detailed water quality monitoring that EcoSource is supporting Umgeni with, which is again is backed by technology from ourselves. So this is monthly water quality as opposed to the weekly one that some of you may be aware of already. What the WaterSphere service does, it really creates a whole integration of water landscape metrics, okay, to help you better understand what's taking place in the surrounding basin, catchment area, shared international boundary, whatever. It's monthly reported intelligence, which is designed to either give you something if you haven't got anything as a water authority, or to augment what you've already got if it adds additional content and information you didn't currently have. One of the great things is it's consistent, detailed content information across whatever target basin or catchment you're looking at. There's no subsection of particular dams or dams or reservoirs and so on. Every surface water is monitored. The whole landscape is monitored in terms of vegetation. The whole area is monitored in terms of rainfall. So it can act as an early warning, decision support, information source. Okay. Again, because we've got historical data inside it, sometimes going back 20 years, you can get a whole range of scenarios to understand the resilience of the system, the impact of changing climate year on year on the system and the water as well. Okay, so it's a very informative, standalone, globally scalable, satellite data-driven information system. It looks like this in terms of a dashboard, very similar to the dashboards that the AMI Insight engine have as well. So this is one where we mocked it up. This is, when I say mocked up, we generated a viable example, operating example over the Umgeni management area. So you've actually got rainfall, you've got reservoir indicators, you've got water quality for selected dams, you've got vegetation condition, groundwater status, and then an overall derived drought index again, all of which can be looked at and evaluated through time, and also down to, in this case, the smallest reporting unit being a quaternary catchment. Okay, so it's very dynamic in terms of its interpretation and its accessibility. All the information is available both then as spreadsheets and geographic overlays to augment and be embedded and ingested into your own systems. So we took all of that together and pulled it into the integrated capability of Insight Engine and WaterSphere. Okay, so the way this was set up as a proof of concept is that the Insight Engine ingested available data that was shared by yourselves and data that we created specifically to mock up this scenario for the actual water authority. So you've got the combination of like logs, reports, PDFs, text, graphic data, and so on. That standard or conventional structured, unstructured database data was augmented and enriched with what we had for water, from water quality conditions, specifically for reservoirs and dams in Umgeni's management area, which we derived from actual satellite data from using WaterSphere 360. And then we use the whole AI processing capability to extract a whole set of information that might talk to certain instances, certain insights, which could be geographically defined, timeline defined, or even in terms of multi-asset association relationships. Okay, so the idea is that the Insight Engine is now providing a very quick end user solution focused set of information which can be accessed through dashboards which have the ability to disseminate that information to you through maps, timelines, and even a chatbot support capability. Okay. And as I said, remember, this is based on a combination of some real data, a lot of dummy data, which we created, and real data from WaterSphere 360. The dashboard that the AMI Insight Engine has 4 key components. Okay, it has what's called a map lens, which allows the user on the dashboard to visualize where certain things are happening. So it's basically problems by geography. It has a timeline lens, which allows you to actually understand what's happening through time. Could be operational spikes, it could be weather dependent changes and so on, and understand, so where is it happening, how long has it been happening, what is happening, and then using all of that together you have what's called a relationship lens, which allows you to actually trace the impact of something back to its root cause quickly, efficiently, and with greater insight that can be normally done through manual processes. Okay, and the chatbot system allows you to come into that and actually look for insights which are not necessarily reported directly in the dashboard, but ask something very specific. Okay, you could, for example, use it to actually look at, please show me all possible illegal connections which are occurring within a geographical region called Durban. Okay, can you link any incidents in terms of system management, system breakages, which could be linked to illegal connections? Okay, and then that could obviously then be used to prioritize the distribution and the actions of field maintenance teams and so on. So it allows you to do dynamic data interpretation, data interrogation over and above what is actually reported in the dashboard itself. Okay. The example we did here was like saying, okay, what equipment is impacted by, say, valve breakage reports? Okay, we can quickly get a list of the models of those pumps or the valves and the site locations. We can see if they have any known level of potential stress under certain conditions, and then that could be used to actually prioritize and dispatch maintenance crews. Okay. What we've done with this one, okay, and this is where the last 2 slides are really the most important kind of content that we're presenting today, is show you what happens if you start linking WaterSphere 360. In this case, we've specifically looked at the water quality component. Okay, so we know that WaterSphere 360, using satellite only data, which has been pre-calibrated, can monitor and give an indication of the water body quality. Okay, so we can actually track algal bloom, turbidity, and other water quality parameters. Okay, we can use that to see, well, okay, is that actually impacting on downstream system capabilities? It could be the clogging of pumps, for example. Okay, and again, you can start to build up a informative set of information and actions to actually give you predictive maintenance and quality assurance as to what should I be doing if this is taking place, or what do I need to do because this has taken place. What we did, and this is probably the most important way of actually visualizing this capability, is to say, well, okay, let us simulate within this system that we have a calendar-based spike in customer complaints, and those customer complaints are linked to water quality that the customer is perceiving or getting in terms of what comes out the tap. So it could be smell, it could be color, it could be taste. Okay, the system will very quickly say, okay, this is the geographical area of where the actual complaints are coming from. Okay, if we actually look at those problems there, we can actually see that they're all linked to a lot of maintenance challenges which are being reported for a certain set of pumps. Okay, if we look back in the system where those pumps are connected to the taps that the people are having complaints with, we can see that it's all coming from Inanda Dam. Okay, if we then look at Inanda Dam in terms of the water quality, we can actually see that exactly the same time frame that these complaints were coming through and we were starting to get pump failures, we actually had a very strong algal bloom. Okay, so therefore you've now got a track and trace insight capability to understand what is happening in terms of cause and effect through the whole system. I'm not saying this couldn't be done before, but this is something that takes a matter of minutes to actually do in terms of actually understanding it because of the Insight Engine AI kind of like insight data dive capability. Okay, so that's what we're trying to show here, is that with these new systems, you actually have the ability to do the same kind of work better and even new work from a new angle, which wasn't possible before because of the complexity of understanding all the different data sets. So what you've actually got then is a way, hopefully what we're trying to show you is that these technologies exist and they can be available to water authorities like Umgeni to consider as a way of actually moving up to the next level of technology support. Okay, I mean you're getting, in terms of Umgeni, just as examples, you can do fast identification of illegal usage, again, through purely predictive linking of data sets that could infer that. Okay, you're getting predictive alerts on possible equipment failures because of something upstream. Okay, you're getting the ability to respond to customer complaints quickly because you can understand cause and effects all the way through. You're getting smarter resource allocation of teams going out into the field to actually hit the problem quicker and more insightfully in one particular area. And also, because you can reverse this, you can actually get a full audit trace of actually what do we do if something happened. We can prove that something happened. Okay, so it really is a way of actually giving another level in terms of cause and effect management insights using these technologies built around the whole AI data integration capability. So what we're trying to show you today, just to finish off with, is that this is something that is now operationally capable. The AMI Insight Engine is already working overseas. WaterSphere is already up and running in several places here as test scenarios. It's really a way of linking human knowledge, earth observation, AI capability for sustainable water delivery. So that is the summary of what we wanted to show you today, just to make you aware of this. Hopefully it piques a lot of interest and a lot of questions, and it's kind of an awareness campaign to show you this is what we've done with your assistance in terms of sharing some data, augmented with a lot of synthetic data to make this whole process possible, and just to illustrate these technologies exist. Okay, thank you very much. Jason, back to you.
Yeah, that's great. Thank you. It's brilliant, Mark. Would you like me to demonstrate some of the dashboards? I've given you a
Absolutely,
link with those. All right, let me just share quickly this side. Please let me know when you can see my screen.
Coming through. Yep, got it.
Okay. So this is the WaterSphere 360. This is directly set up with the Umgeni area of sort of influence. So we've taken Umgeni Usutu, Umgeni Mhlutuzi water sort of area of sphere of influence. So these are all of the catchments that are kind of running through Natal. And we've got several different sets of indicators that you can have a look at. So the idea over here is this kind of takes you through a drought cycle, but we can also do similar things with other indicators related to that. So the first thing over here is having a look at their meteorological sort of indices, and we've got different indicators for your meteorological elements. So rainfall SPI, which is the spatial precipitation index, and all that is a normalized index of your spatial precipitation, and it's comparing your normal climate conditions against the actual sort of rainfall that's recorded. So we've done this, and it finishes in December 2024. But what you see over here is a stacked set of information, and this is taken directly from the chirp state, I think it is, in South Africa, and what you base or across the globe. But this is for captured for these catchments across South Africa. So what you see over here is Gainey area, and anything that's in the sort of orange band is in the lower sort of areas over here, and anything in the sort of green to blue bands means that the water there's higher than normal rainfall. So green band is normal rainfall, and then anything in the yellows and orange is low rainfall, and anything in the blue, etc., is higher rainfall. So you can see these areas over here, at least in that December period, are looking at dry, and then these areas are above normal rainfall in the sort of north areas there. And this is captured for different indices of SPR. So SPR 1 month is 1 month spatial precipitation index. There's a 3-month one, which you'll see changes the picture slightly. Then you have a 6-month one, which is a longer term sort of period where you're having a look at the rainfall average over the 6 months. 12 months is a yearly one, and then 24 months is higher than that. So you can see when you had that 2018 sort of drought, that there was quite an extended period of drought prior to that in terms of low rainfall, and then it goes higher. And you can actually change these values. I'm not quite sure how far back this is stacked to. I think that'll go all the way back here. So there we go. So you're looking back to, I think this goes back to about 1985, if I remember correctly. So you can change the different elements and have a look at a sort of analysis related to that. So that's the one rainfall indicator. The second one that we've got is also similar to the SPI, except that it's now stacked with the seasonal variability. And what you've seen over here is the changes of the actual setup with standard deviations put in place. So the black line is the measured, and then you've got standard deviations beyond where you are. So it's the same data, it's just a different way of representing it. And then finally over here we've got these slightly more conservative representation of the rainfall. So again, you can see the rainfall seasonality, where it captured the sort of highest events in specific years and the lowest events in specific years. Again, the black line shows you where you're tracking against that particular marker in terms of the measured rainfall over that period of time. And what you've got over here is these are percentiles. So they're not standard deviations that you're looking at like in the SPI. It's different percentile ranges that you're having a look at. So anything in the sort of green areas up there is in the sort of upper 70th percentiles. Then you get down. And what you'll see over here is this variability obviously disappears. So this is the 1 month. But if we go to, for instance, 6 months, you'll see, well, we'll still get some trends there that starts to flatten out. And then when you go to something like 24 months, you'll see it's even less than that. In fact, it's almost flat. Okay. But it gives you an idea of when it was sort of dry and wet, and you can sort of track those elements quite easily. Then the next element that you're having a look at is, okay, I've gone on to, just going to have I missed vegetative? Let's just go back to this one. All right, so vegetative analysis is what we've got as the NDVI. On this setup, you can actually do a start tour so that you can actually go and have a look. It'll show you different components of where to click and those types of things. And if you don't want it showing again, you can switch it off. I'm not going to go through that. This is the NDVI. So here we've got it stacked with things. So this is the normalized vegetation index. So this gives you an idea of what condition you've got in terms of the actual vegetation. So the idea is that the rainfall, the deficit in rainfall will then start to reflect as a deficit in your plant conditions in a specific area, and you can have a look at that. This again is stacked, so all means the overall NDVI, so the vegetative index or normalized vegetative index. We've stacked that for cropland, so that'll pick up cropland area. So anywhere in grey, there's no real crops in there, but then anywhere in these other areas that you see is they've got information for cropland. Same with grassland, shrubland, and tree cover. So this gives you an idea of the vegetative conditions of those different elements in there. So quite often tree cover, for instance, will take longer to respond to a deficit than grass cover. So you can start to see if there's sort of stresses in the system and how that's sort of permeating through. The next one is water resources. So what's interesting over here is you've got two sets of information related to the water resources. So you've actually got the satellite captured aerial extent. So Mark's team generates the aerial extent over here, and then you can compare. So we've got the maximum extent. Now this is the maximum extent. This is with Sentinel-2. So it's only captured from 2016 onwards when those sensors were put up in the sky. And then you can measure that against a specific period. So let's go to your 2018 sort of drought, I think, over here. And let's try and change the color here for you so you can see it a bit more prominently. So there's Albert Falls, so you can see, and we can just switch it off the opacity. So there we go. So the maximum extent is the blue area, and the red area is that 2018 extent that was captured. You can also compare it to different things. So if you're wanting to say, let's say, having a look at the 2024 period, it's just you can see that it's slightly different there. So you can compare the different elements related to that. And then you can click on the dam itself, and it'll give you an idea of the volumes associated with that. So you can see that that 2018 period, when you had the drought, was obviously very low. Then you got some recovery, and then we had some good rainfall in 2022, which resulted in that sort of coming back into normal. So you can have a look at the different dams and see how they were performing. I think one of your main concerns there was it Hazelmere? I can't remember. In the thing, so yeah, that was tracking very low. It still hasn't quite recovered according to these estimates here. So that gives you an idea of the water resources. So again, following that drought cycle element, once you get vegetative deficits, then you start to see that reflecting in the water resources, and you can have a look at it and see the different individual dams. Similarly, I actually got that stacked already. Similarly, you've got the groundwater status associated with this. So this is captured from the GRACE satellite, which is a gravimetric sort of method, having a look at it. And the main changes that you get in a particular area are related to water volume fluctuations from those different aspects. And there's a set of algorithms that they run through to generate this using satellite GRACE satellite configuration, but it's run on a GLDS configuration. So you can then see the relative sort of system components related to, for instance, groundwater in a particular area, and anything in blue means that there's more than the average amount of groundwater that's been recorded over history in that area, and then anything in the sort of oranges and reds would mean that there's a deficit of groundwater compared to the recorded history. This goes back quite a long way. I'll just try and find out how far back it goes. Let's see. Just gonna. So we've got that stacked to about 2006, but I actually think it goes back to around about 2000, if I remember correctly. So you can see how the groundwater sort of values have changed. And again, you can see very low values in that 2018 period related to that. In that particular catchment, it will change from catchment to catchment. So you can see this one, there's much longer deficit there. All right. So that's the groundwater status that is separated into three different components. So you've got the groundwater. You can also have a look at a root zone, which is just obviously the plant root zones related to that. It's a bit more variable in those scenarios and responds a bit more closely with rainfall. And finally, the surface moisture is the last one. That's the most variable of the two. And again, this tracks quite heavily against what you would normally see with an SPI. Water quality, we've got a number of dams that have captured in terms of water quality. I think I've actually got that stacked here. So yeah, you can have a look at various dams, let's say in Nanda, and you can have a look at different components related to this. This we are still working on quite a bit. The Sentinel-2 indicators we've got a fairly good handle on. The Sentinel-3 seems to be fluctuating a little bit more than we would have expected and giving us results in certain dams that are a little bit different. What we've discovered is there's a turbidity component which makes if you've got low turbidity in dams, it actually over-reports algae and chlorophyll concentrations in certain areas. So we're adjusting some of those. But you can have a look and click on a dam and see how it's tracking in terms of the water quality index, whether it's something that's good, bad, or sort of ugly related to that, or in this case, very low concentrations of algae, very high. Turbidity, we actually a lot better with in terms of the turbidity measurements in these different dams. And then we have put phosphate and total organic carbon, but we're probably going to remove those. So we'll focus on algae, turbidity, coli, and chlorophyll status related to that. So that's just the water quality indicators, which give us some sort of idea of the water quality in a particular dam resource. Like I said, we're still working on this one because it's not quite right at the moment. And then finally, we've got an overall drought indicator over here. This gives you an idea of the performance of the sort of system with all of these different indicators. So we've got a set of indicators that are ranked over here. So you've got short-term rainfall, then we've got a medium-term one, which is about the 6-month rainfall, if I remember correctly. Then we've chosen the groundwater index, the soil index, the root index, and then we've got a sort of index related to the different systems. If you've got a large dam that influences the system, there's a different scoring to whether you've got medium and then small sized dams in different catchments. And that information is captured and then put into this drought index over here. It runs on scoring system that is it's not quite an MCDA, but it's very close to an MCDA, which is a multi-criteria decision analysis. And what you do over there is you actually score the different components of the drought index into a scoring system that'll go from in this particular 0 to 10. It can be 0 to 1, it can be 0 to 100, doesn't really matter. But you rank all of these elements into those scores, and then they weighted together in a certain set of ratios, and that would give you your overall drought scoring. And this can be changed. We've obviously picked these particular elements, but obviously with the discussion with somebody like Umgani Water, that would give us some sort of information related to the drought cycle, and also potentially a sort of flood cycle if you wanted to have a look at those elements there. So that's essentially the dashboards, and we'll see how these things sort of vary over time. I don't think we can go beyond 2016 here because that's when the Sentinel stuff started going. But if let's zoom into your Pietermaritzburg areas here and have a look, I think you'll see that 2016, 2017, 2018 drought was quite severe, and then you start to get better results with 2023, 2024 sort of popping out there. And again, these indicators we could make more or less severe according to how you want to rank these different elements there. So that gives you an overview of the WaterSphere 360 sort of system that we're running. It's obviously well, we've researched quite a lot of this and captured it, so pretty confident with the meteorological, vegetative, water resources, groundwater status, water quality. We're still doing quite a bit of work on, but that gives you an idea of what is done there, and then this would feed into something like the AMI Insight Engine or other information that you've got in different areas, which will help you perhaps with your water resources management. Thank you. I think that covers everything from my perspective, and I'll open the floor for questions for the next 20 minutes. We don't have to take 20 minutes, but yeah, please let us know what you think.
Jason, there's a question in the chat. Sorry.
Okay, yes.
Thank you very much for putting this together and stuff. I don't know, guys, are there any questions, please? Because speak now. Otherwise, Jason, you mentioned that you've put that dashboard on, or you've given us access to that dashboard, even though it only goes up to December 2024. But at least then we can have a look at it. The guys can spend some time to go through it.
Yes. Yeah, so in the chat, there's a link there. The dashboards can be accessed via that. It's called ecodata.co.za, and that would enable you to have a look through that. Yeah, and then in terms of the water quality monitoring, you've got a question here from Nathaniel. So the water quality monitoring info presented is limited to dams. Have you tried water quality monitoring on rivers? And do you have some river abstractions? Fortunately, and there's some sensitivity to changes in turbidity, etc. So the answer to the first component, I mean, Mark can talk about it a little bit more, but the Sentinel-3, which is the one that's been used for this particular set of information, is the resolution's at 300 meters. So the answer is that we can only monitor larger and bigger dams associated with that. Even the Sentinel-2 is a 20-meter resolution, which we are actually monitoring some of your dams in Umgani for, and that Sentinel-2 allows us to have a look at smaller dams, etc. But it's still too coarse to have a look at rivers unless they're very wide, which is not the case in the Umgani system. So we can't monitor the river water quality. And then, yeah, just to give you an idea, Nathaniel, we have got some water quality measured information from Umgani water, and we've been correlating and with that, so that we've been trying to capture that measured data and reflect it in the assessments. Yes, Mark, go for it.
Sorry, yeah, just two things. One is just to double check, are the access to dashboards being controlled through the password allocation? I wasn't sure that's still going through Lorraine, or was that direct now?
I know that the password allocation's only been switched on for those Portugal areas.
Okay, all right, that's fine then.
This is open to access at the moment to anybody who's got the link.
Yeah. Okay, right, and then just to add on to the water quality one, what we have done in response to the same kind of question, because we've got the similar platform operating in Portugal, obviously the resolution, as Jason indicated, even with Sentinel-2, isn't ideal for narrow rivers. But the one way of building that river length knowledge is looking at the water quality of a dam upstream and the water quality dam downstream. And obviously then the river section is likely to be the worst of those two. I can't quite see the rest of...
Nathaniel's got another question there. So
okay, that's yours then, Jason. That's the calibration against the in situ data.
Yeah, so at the moment, Nathaniel, there's with Futi's group with Ntando, we've set up a system that generates weekly images of water quality across across all of the dams. Or there's 12, I think, dams in the Umgani Umhlathuze water system. I'll have to get the names of those dams. I can't remember them straight off my head, but it's your main dams that are having a look at. So it's everything from your sort of Henleys and those types of things. Then obviously Midmar, Albert Falls, Springgrove, Mearns, all of those. That captures the water quality, and that has been calibrated against measured water quality. I'll send you, there is a report. It's quite a large report. It's several hundred pages long, I think, but it gives you an idea of the calibrations associated with that. In terms of picking up the water quality, we're able to pick up the water quality for turbidity and Secchi disk quite effectively. So that's your sort of parameters, quite well linked to visual markers. Other aspects that we are able to pick up, so we are able to pick up algae and those types of things, but those are not quite as easily parameterized, if you like, against that. So what we've done is we've developed qualitative indices related to those. So it gives you a good idea if it's good, bad, or ugly, but it definitely can't give you sort of exact precision sort of measurements on those. What we have also discovered is there's a turbidity element, which I think I mentioned earlier. So if you've got a highly turbid dam, the indicators seem to be different to if you've got quite a clean dam. So, for instance, Midmar over reports versus these other systems here. There, I think Mark is showing you some of those pictures related to it. So there's Midmar, and you can see some of the areas where you've got inflows and water quality elements related to that. So that's the 20-meter sentinel, and that reports on a weekly basis. If there's cloud cover, it won't report it. And then the Sentinel-3 stuff, which you've seen over here, we're working on just recalibrating a lot of those to those indicators and stuff like that. Yeah, so that's the kind of thing that you've seen, which Mark has shown you in the chats there. And I can actually take you through a more detailed setup related to the water quality indicators on that, but I think that's outside what we're showing you over here. All right. I think that hopefully covers your questions there. And yeah, are there any other questions? All right. My suggestion is please have a look at the website, go through it, give us feedback where it's because these are all sort of work in progress. Be aware that if you do find this useful, we can operationalize this actually very quickly. Most of the indicators are able to generate within around about a month. And yeah, I mean, if you're interested in that, we can look at that and discuss some pricings with you related to these, if these are important for your systems, and we can then make it available to yourselves internally through the password protection, but also allow that to be shown for public consumption, if you like. Thanks. Go for it, Mark. Yeah.
Sorry, Jason, just to qualify, that comment about the months. Okay, we normally estimate for whatever target catchment or basin area we're setting the system up about 1 to 2 months to implement the system. Thereafter, it's monthly updated going forward. But because we've already got 90% of the history already done, and we're only missing basically from December 2024 to current, the implementation time would be significantly less as well. Okay, thanks, Nathaniel, for checking. Okay, that's great to know. Thank you. Okay, sorry, Jason, thanks.
Well, thank you.
Sorry, Jason, I put my hand out. I don't know if you could see it.
No, sorry, Graham. No, I didn't see it. Go for it.
Yeah, just a quick question. I don't want probably quite complicated, so I don't want to drag out the meeting. So how does the satellite measure the groundwater? What is it measuring before I can say how does it work? How does it work in relation to the groundwater? I don't know, porosity or yeah.
No. So I mean, that's a very good question. It's so the GRACE system runs with its two satellites that kind of run in line with each other, and as they pass over specific areas across the globe, they influenced by gravity, which either slows them down or speeds them up. And what happens is you get this sort of gravitational anomalies that are detected by the satellite, and then that is taken down and translated into shifts related to those gravitational changes are generally related to water movement across specific areas. So then they take that and they have a look at that, and then they translate that through into these GLDAS algorithms to have a look at how that particular sort of gravimetric information translates into the sort of water cycle. And then they also have a set of other information related to rainfall dynamics and stuff like that. So they've got a model that's related to that, that then separates that out into groundwater, root zone, and surface water. So it is quite a complicated procedure. I'll send you the links to that, but it's mainly based on that gravimetric GRACE information and modeling data. So they use the GRACE information to look at that. You're not going to get a specific well point in a particular area. It's over larger areas. So you're looking at sort of 50 to 100 square kilometer sort of changes. So it's fine at the quaternary catchment level that you see over here, but you're not going to see it for a specific well. What we have seen is I'll get you some papers on it, but the GRACE information compared to actual measured data in certain of the areas in South Africa, and that while it doesn't show you precise information, that tracks the trends quite nicely in terms of your background information. So you've got an idea of kind of what's happening in an area, but it's not precise. Yeah.
Okay, that's great. Thanks very much.
Pleasure. Yeah. All right. Are there any further questions? Do you look at water storage dynamics? Linda Kulu, can you just perhaps expand on that a little bit more? Okay, you're typing.
Yeah, there's typing typing coming through, Jason.
I've shared again here, Linda Kilo. So sorry, I'm just trying to get to your reservoir indicators here. So in terms of water storage dynamics, let's click on another one, maybe Ananda, for instance. You can see how it's tracking against the sort of history related to that, and we give you a fairly good history of how it's changing over time. And then what you see over here, these different colors are related to different levels in the actual dam against recorded history. So you can get an idea that, for instance, 20% of the time, Inand has been lower than that red line, and 20% of the time it's been that sort of blue zone over there. So those are stacked in terms of future water dynamics, in terms of extrapolating going forward. That's not in there at the moment. It is something that we are going to look at in terms of projections associated with these things, but it's not something that we've got in at the moment. And I think you've already got some of your dams on the systems kind of already stacked against, let's say, the water resources yield and planning models, and you get those trajectories going forward. So we can certainly capture some of that information, but it's not to that level of detail. What it does do, though, is it monitors all of your dams right across the system. So at the moment, you've got information on your larger dams, but you can actually see, for instance, medium-sized dams is anything above the 25,000 meters cubed level. So you can get an idea of what the smaller dams in a particular catchment are versus different areas. So you can get an idea of the water dynamics in the system as it's changing compared to certain periods in terms of what their average sort of water fullness is, if you like. So I hope that helps. I don't know whether that's answered your question. Mark, you've got your hand up again.
Yeah, I was just going to make the added sort of comment and caveat that in terms of monitoring, using image detected surface water extent to derive then the dynamics of volume over time. One thing we can do is ensure that we have within the month a cloud-free wall-to-wall, coastline-to-coastline representation of surface water, as long as surface water is the primary surface that the satellite sees. We use radar data to complement the optical data if there's cloud, so it's an all-weather capability. Having said that, though, if there is floating aquatic vegetation, if there is water lettuce, if there is hyacinth and so on, okay, or even dense emerging rooted vegetation where we cannot see the surface water, then that will distort the modelling process. We know for a fact that in places like here on the Highveld, Bronkhorstspruit Dam, Hardebeesport Dam and so on, that with the floating mats of water hyacinth, you do get some very strange water obscured patterns taking place month on month, which will influence then obviously the volumetric areas. So if you've had a massive long-term month-wide flush, for want of a better term, of water hyacinth or water lettuce, that will impact the way in which the volumes are reported. That's a global phenomena which we can't get around at the moment. Okay. Jason, you're mute again.
Sorry, thanks, Mark. Is there somebody else's hand up there? Okay, so yeah, I just wanted to show you that you can sort of see information that's captured for different sort of periods for your smaller resources as well. So you can see in these areas over here, red would be your 2018, and you can see some of these dams have not even, there's no water in them or very little water in them in that 2018 period when you're having a look at it. And I guess Daniel's question is you can pick up some of the river sections on these setups. But you can see that 2018, a lot of these dams were much lower than that is. And again, it's a little bit of the pixel resolution is not great, but you can get an idea of the overall sort of water quality of, sorry, not quantity of these different smaller dams across the country or across a particular area. Yes, Graham, go for it.
I just saw some center pivot irrigation there. Would you be able to estimate the amount of irrigation as a volume taking place in a catchment, and then obviously then if you're so inclined, you could compare that to licenses issued in that catchment, and obviously various, that would be quite a useful tool to determine abstraction rates in the catchment and also your water balance. Is that something that's doable?
Yeah, so not part of this system, Graham, but Mark and I actually, I mean, one of the reasons that we started to work together was on these projects, which were verification of existing lawful use. And certainly there's a couple of products where we are looking on combinations of these types of elements. So there's a system called GeoFarmer, which is a more detailed application related to irrigation identification over specific areas. And certainly that's something that GTR could use to estimate the water use with different areas across different sets, and also verify whether things are being irrigated or not irrigated in those areas. And then what we've actually been looking at doing is linking that to some of your water resources to understand what your water takeoff is in those different areas. So you can't do it with this product that you see here, but it is certainly something that we are doing and have done.
Just to add to that, Graham, the GeoFarmer gives you within field sub-weekly intelligence on crop growth. And what they've developed linked to that is what's called the irrigation scheduler. So it's the optimal allocation of water in a particular pivot or pipe system according to the growth and the rainfall as well. And then, as Jason said, you can scale up from that to water usage and water requirements.
But yeah, we'd have to do a different presentation to show those capabilities. That's a presentation in its own right. Yeah.
Yeah. I think just as a parting comment on all of those, Jason, is that all of these systems we're talking about, whether it's the water sphere, whether it's geopharma, irrigation scheduler, they've all been designed as scalable solutions. So they are in essentially drop and play capabilities. So whether you're doing it over Umgeni's area of interest, whether you're doing it over an area in Estonia or an area in Brazil, they all work. They're scalable solutions. That's what's been, so that they've been designed not to be location specific capabilities.
Right. So I hope you found that interesting. Please look at the system, and yeah, your comments are welcome. And yeah, we look forward to any feedback that you give us. We have finished the hour. We will circulate some minutes and notes related to this. And yes, thank you very much for participating. And yeah, enjoy the rest of your day.
Thank you very much, everyone. Thank you.
Thank you very much.
Thank you.
Thank you. All right. Cheerio, everybody.
Bye.
Thank you. Thanks very much for organizing.